Hey folks, welcome to Advent of Code in F Sharp, day 18. This will not be a live code. This will be a summary of what I did to solve it, because for those who watched my Twitch streams, we were chugging along pretty nicely actually for day 18, until we hit on the part where we had to explode our snail numbers. So that's maybe a bit Chinese. Let's drop to the explanation. But there was a little part here called exploding. We needed to explode snake numbers, and that really broke my brain because we had to go back in our recursive data structure, and it took me a while to figure out how to do that. But I did, and I wouldn't want to summarize like my solution, because actually I really like the end result. I used I think 3-4 intermediate or advanced concepts that I would like to show you, because I don't use them in the day job, and it's fun to play around with, and it's fun to explain them. So here we go. Day 18. What did we have to do? We had some snailfish numbers, but if you squint just hard enough, you see that these are actually binary trees. So a number can be a raw value or a pair of two other numbers, and it's recursive. And we had to do some mathematics on it and some reductions of intermediate results. And that's where my brain got wrecked. So let's drop to the F# code. Yeah, there we go. You'll see a couple of libraries here. The unquote library we see every day. That's my assertion library for writing my tests. But fparsec and fscheck are new. I don't think I used them this year, so we'll quickly go over that. But first, let's take a look at what we did. I encoded my binary tree in something called a number, a discriminated union. So it's either a value or a recursive type with a left and right branch. I called that pair. And you'll see something else here. It's depth. It's not necessary, but it made my life a bit easier to check when we needed to explode something. Every node also knows its current depth. So that's what I mean by this. Then there's some helper functions. And then the first interesting thing is called Parser, because we use a Parser library called fparsec. It's a clone of a Haskell library called Parsec, I think. And it's really cool if you have like these grammars or recursive grammars, even like we have here. You can write your parsers in a very declarative way, at least if you figure out what all these magical operators mean. On stream, it took me, I think, an hour to hammer out this parser. But in the end, actually, it's what? 1, 2, 3 lines of code to write a recursive descent parser in F#, which is pretty cool. Maybe quickly a summary of what I'm doing here. I'm building little parsers and combining these parsers into bigger parsers until we have the parser for snail numbers, basically. So you'll see a parser here called snail number. That's the big one. This parses the entire recursive structure, and it's composed of two smaller parsers, which is this p-value parser and the p-pair parser. And those literally translate to the two rules in our grammar. The p-value parser parses integer values, so just those single-digit numbers. And the p-pair parser parses stuff between brackets. And you see here what's between these brackets. Those are snail numbers, so we recursively call that top-level snail number parser when we are parsing a left pair or a right pair in a pair. And we need to do some black magic in the highlighted orange thing here, but if you are interested, you can look this up in the fparsec documentation. It's not the best documentation in the world, but it does the job. And here you see I combine those two little parsers into one bigger parser with an or, so it's either a value or a pair. And yeah, that's it. That's parsing. So that was really fun to figure out. Not live, but when we had the parser, it's always really satisfying to take a look at. Writing one is hard work. But that was the easy part. We can parse into recursive data structures now. And then we had to reduce or simplify those binary trees with the explode and split rules. Yeah, so these explodes and split rules. And going back after an explode to like add a number to the left subtree, that was breaking my brain. Until I like remembered reading about something a long while ago while I was learning about Haskell. I'm not a Haskell pro, but I read some books about it, and this is one of the most familiar books. The humor, you gotta like it. Not everyone likes it. It's like tongue in cheek, but it's an acquired taste. But the contents of this book are awesome, and especially for this day, chapter 14 on zippers. That's what made me have like an aha moment to solve the snail number puzzle for this day's Advent of Code. What's a zipper? A zipper is a way to traverse a data structure, like a binary tree, what we're doing here, while remembering the context. So let's take a look at how they phrase it here. But here they phrase it like you can traverse a binary tree, and every time you go deeper in that tree, you leave a trail of breadcrumbs. So you remember whether you took the left sub-branch or the right sub-branch, and you remember the entire path up until the node where you're currently at. So if you look at what a zipper actually is, type-wise, you see that here. This is a free online book, by the way. I'll put a link in description so you can read it at your own leisure. But what is a zipper? A zipper is just a combination of a subtree. This is like the current node where you are, and a list of breadcrumbs, which is basically the path from the current node to the root of the node. So for every decision you make, you remember, did I take a left turn or a right turn, and what was the other branch like? And this data structure allows you to do stuff in a tree, but also like to remember how to get back to the top or how to go somewhere else in that tree. So that's zippers in a nutshell. That's very abstract. Let's play with them for a bit. So you'll see here, I wrote a lot of zipper code. I think I spent the better part of an hour writing all these zippers. There are implementations and libraries for zippers in F#. I found one in the F#X collections thing. Let's take a look. Or at least I saw that the zipper was mentioned there. Binary tree zipper, yeah, that's, I think, literally what I implemented. That's the original paper discussing the zipper abstraction, yeah. So it exists, but because I did not know about it, or I never used the zipper, I found it fun to write one myself. So this is what you're seeing here. I'm not going to go through the implementation. It's literally the things from the book, but I will show you a couple of use cases how you can use zippers. So let's go back. Yeah, so this is what my parser API looks like. You provide a string and it parses into that binary tree. So we have a binary tree now for the pair 1, 2, 3, 4. So it's a balanced binary tree with 1, 2, 3, 4 nodes. And let's play with zippers. So we just explained the basic concept of a zipper. It's like a way to traverse the data structure and remember the route you took. So let's try navigating a zipper. What do I mean with that? Let's make a zipper of a number. So this makes a zipper out of one of those snail numbers. And that is actually, when you just make a zipper, it's the data structure where we are at right now, which is the root. So it's the entire tree. And this is the breadcrumb trail, which is an empty list. We have not taken any steps. So let's take a step. Let's try to traverse to the left of the subtree. So I wrote these helper functions left, and this will take the left subtree. So if you look at what happens now, you see that it returns an option, but let's forget about options for now. You see that we're currently at a different subtree. So we are now in the 1, 2 subtree, which is this first pair. And you see that the trail of breadcrumbs has grown with remembering the decisions. So this means we took a left turn, and this is the other subtree. So this is the right subtree. And by keeping track of these breadcrumbs, as you can see here, let's maybe take one more step. So I'm going to break out of option world. Bad idea to do this in production code, but never mind. And let's take another write. So now we are at this 2 in theory. Yeah, so now we are at this 2, and you'll see that our breadcrumb trail has grown. We first took a left, and the last thing we did was took a right, and this was the other subtree. That was that 1. So this is the zipper in action. You can do stuff when you're at a location in a zipper. I wrote an apply function to apply a function on the current node. So let's say we want to make this current node into something else. So we want to have a value node. Value, I don't know, what's a good Christmas value? 25. And a depth, I don't care. It's option again, so I'm going to break out of the option world. There we go. So this applies replace. So this replaces the current node in a zipper. And you'll see here, current node is now value 25 at depth 0. Depth 0 is super incorrect. And I had some bugs with the depth, so I'll just fix this. But you can change stuff in the zipper, I mean. And if you do zipper.top, this zips the entire zipper back onto the root node. And as you can see, this reconstructs the tree as it was, but in there is the 25. You can make this easier by just getting rid of the zipper abstraction. This 2-number thing zips to the top and gets rid of the empty path, so we're just back into the number world. And you can print this. I have a function print that prints out snail numbers. And if you take a look at this, you can see that we replaced one of the subnodes. So the 2, we replaced that with a 25. And that's basically what you can do with zippers. And it was really useful for this day. I wrote one more function that's worth taking a look at if you want to do this yourself. It's called left sibling. Yeah. So if you have a zipper and you say, let's go left. So actually, let's go back to where we were. That will work better. So let's go left, let's go right. And now we are at some place. If you do, or let's first show where we are right now. So now we are at the 2. And when you explode, you need to do something on your left and do something on your right. So if you use these little utility functions called left sibling and right sibling. So try left sibling. This zipper navigates to the leaf node on the left, so to the 1. And that's actually the only thing we need to explode in a cool way, or in an easier way than not having a zipper as an abstraction. So zippers, I have come to love them for tree navigation, where you have to go back and forth tree and not only recursively descend. So that was a really cool lesson. I have never worked with zippers. Today was a great example of when you could use them. So we discussed parsec, we discussed zippers. There was a third thing I wanted to quickly highlight, but it's not a huge deal. It's fscheck. If you have not heard of fscheck, it deserves some love and attention. So I'm going to show you what it does. fscheck is a library that allows you to write property-based tests. And a property-based test is orthogonal to a unit test, like we all know them. So these are unit tests or example-based tests, where you give a concrete example. So for example, here we say parse this thing, and it should be this tree. That's a nice way of writing tests, but now you have to write all the tests yourself. Property-based testing provides you with a different approach, where you don't really provide the examples, but you provide properties. And a property is like an invariant about your code. For example, an invariant I wrote here is saying traversing a zipper leaves the number abstraction that the zipper is traversing intact. So if you see here, this is just a function that takes a left subtree, a right subtree. We build a pair or a tree from those two subtrees. And then we do some random walking around. So we zip, we go left, we go up, we go right. And then in the end, we say, okay, zip all the way to the top and rebuild this as a number. And this property, so it takes two subtrees and it verifies that if we make a tree out of these two subtrees, and we walk around in it for a bit, those should that should be the same number as the initial number. And what property-based testing does for you is you just write this property or this predicate function, and the framework will call your function for 100, 1000 times. You can configure it, but it will try to break your property by providing random data. So it'll call this function 100 times with random right and left nodes, and it'll try or it'll notify you when your property breaks for some random input. So yeah, that's a very cool way of dealing with complex stuff like this. Writing unit tests for all my zipper functions would have been possible. It would not have been fun. And writing a property like this was very fun. So I can recommend taking a look at property-based testing. In general, fscheck is one library, but there's more. And that's the summary of day 18. I don't know if we want to go over the implementation. It's available on GitHub if you want to, but as you can see, there's a lot of nonce, there's a lot of zipper try lefts. It's not super complex, but without a zipper abstraction, I wouldn't have started. So my constraint of not using mutable data structures was a bit of a pain or an extra challenge for day 18, but the zipper abstraction actually made it very feasible and very fun to work with. And fast, actually. So my part 2 solution takes 2 seconds. That's not too bad. Yeah, that's it. That's all I had for day 18. I'm really pleased with the way I solved it. I hope you learned something, or you enjoyed this video at least. And I will see you next time on Advent of Code in F#. Bye-bye.